I'm Cyrus, and today we're going to be going over expected value. Before we begin, I'd like to review some background knowledge. If you feel comfortable with basic counting techniques, feel free to skip this part of the video. Often called committee forming, combinations describe the area of combinatorics concerned with counting a committee from a group of people. Let's look at a simple example. In how many ways can 3 people be chosen from a group of 7 people? For the first person, there are 7 ways to choose them. For the second, 6. For the third, 5 ways. This gives us 7 times 6 times 5. However, we must be careful because we do not care in the order that these people are chosen. All we care about is the 3 people in the end. Therefore, we must divide by the number of permutations of these 3 people. This gives us 35 ways. A more general formula would be n choose r. This means n factorial over n factorial times n minus r factorial, where n is the total number of objects in the set and r is the number of objects that you are choosing from the set. In this case, this formula would give us 7 choose 3s, giving us the same value before 35. Now let's move on to expected value. First, the definition. Expected value can be thought of as a generalization of the weighted average. To put it formally, is the sum of the probabilities of the outcomes times the value of the outcomes. The formula is shown below. The closed form would be P1x1 plus P2x2 all the way to the probability of the nth event happening times the value of the nth event. Also note that the sum of the probabilities must equal 1. This formula looks more complicated than it seems. Let's look at a simple example to get a feel for it. Let's say that we are flipping a fair coin, and if we get heads, we win $10, but if we get tails, we lose $5. What is our expected winnings on each flip? Well, let's apply our formula. The probability of flipping a heads is 1/2 times our winnings $10 plus the probability of flipping a tails 1/2 times our winnings, which in this case is actually negative $5. This would give us $2.50, the expected value of each flip. But let's look at this problem intuitively. Let's say we flip the coin 1,000 times. We would then expect 500 heads and 500 tails. Our net profit would be 500 times 10 minus 500 times 5, which would give us 2,500. Now let's divide by the number of flips 1,000. This gives us 2.5, the same value as before. Let's review some introductory problems. Number 1, what is the expected value of a dice roll? Well, we have a 1/6 probability of each event happening. So it would be 1/6 times 1 plus 1/6 times 2 all the way to 1/6 times 6. This would give us 3.5. Note how the expected value is simply the average of all the outcomes, since the probability in this case is identical for each outcome. Also note that 3.5 cannot actually be rolled, but this is simply an average of all the outcomes. Next, a 6-sided dice is weighted so that the probability of any number being rolled is proportional to the value of the roll. What is the expected value of a roll of this weighted die? For example, the probability of rolling a 2 would be 2 times the probability of rolling a 1. So, let's represent the probability of rolling a 1 as P. The probability of rolling a 2 would be 2P. The probability of rolling a 3 would be 3P, all the way to 6P. If we add it up, this should equal 1. Solving P is 1 over 21. Now, let's look at what this question is asking. The expected value of a roll of this weighted die. So, the probability of rolling a 1 is P times 1, plus the probability of rolling a 2, 2P, plus the probability of rolling a 6, 6P times 6. Summing this up, this equals 91P. But P is 1 over 21, so we simply substitute and get the answer as 13 over 3, or 4 1/3. Next, let's look at the 2021 Fall AMC 10B question number 16. 5 balls are arranged around a circle. Chris chooses 2 adjacent balls at random and interchanges them. Then Silva does the same, with her choice of adjacent balls to interchange being independent of Chris's. What is the expected number of balls that occupy their original positions after these 2 successive transpositions? I've depicted the situation in the bottom left. First, let's note that Chris's choice actually does not matter, because whichever pair he chooses, we can always rotate our situation so it looks exactly the same. Next, let's move on to Silva's choice. There are 3 cases. Either she chooses the same ball as Chris. For example, without loss of generality, let's say that Chris chooses A and B. If Silva also chooses A and B, all 5 balls would occupy their original position. If she chooses AE or BC, 2 balls would, or if she chooses a pair of balls that are completely different from Chris's, 1 ball would occupy its original position. Let's translate this into expected value. For the first term, 5 balls would occupy the original position times 1/5, because Silva has 5 choices to pick a pair of balls and only one of them would satisfy our first case. 5 times 1/5 plus 2, which would be the two balls occupying their original position, times 2/5 plus 1 times 2/5. This would equal D 2.2. Let's move on to some intermediate problems. To begin, let's look at the linearity of expectation. First, let's define it. The expected value of the sum of random variables is equal to the sum of their individual expected values regardless of whether they are independent. Remember, this theorem holds even for events that are dependent. At the top, the formula is shown. The expected value of a1 plus a2 plus an would equal the sum of their individual expected values. Let's look at a very brief example. What is the expected value of the sum of two dice? Well, the expected value would just be the individual sum of the expected values of dice. And we already derived before that the sum of the expected value of the roll of a dice is 3.5. 3.5 plus 3.5 is 7. Next, let's look at problem number 13 from a mock Amy. In his spare time, Richard Royzik shuffles a standard deck of 52 playing cards. He then turns the cards up one by one from the top of the deck until the third ace appears. If the expected number of cards Richard will turn up is n over n, where m and n are relatively prime positive integers, find m plus n. First, let's visualize our situation. Imagine spreading the deck out. We would have A cards before the first ace, B cards before the second ace, C cards before the third ace, D cards before the fourth ace, and E cards after the last ace. A, B, C, D, and E can be any number from 0 to 48, and they obviously must sum to 48, because there are 52 cards in total. Now, we are only concerned about the third ace, though. We see that the expected value of the third ace would be the A cards before the first ace, plus the B cards before the second ace, plus C, plus 3, because we need to add the first ace, the second ace, and the third ace, which are 3 cards. Now we can apply our new theorem to get our answer to be the expected value of A plus the expected value of B plus the expected value of C plus 3. Note that A, B, and C, again, can be any number from 0 to 48. Now, let's try to evaluate that. The probability of any non-ace cards, let's say for simplicity the 4 of hearts, appearing in group A is 1 over 5, because there are 5 groups, and the probability is evenly distributed. So, since there are 48 non-ace cards, the result of the expected value of A is simply 48 times 1/5, which equals 48 over 5. This result is symmetric and produces the same result for the rest. Now, we can finally evaluate our expression. We get that it equals to 48 over 5 times 3 plus 3. Now we can see that m plus n equals 164, giving us our answer. Let's look at our final problem. Peter repeatedly flips a coin until he gets 2 heads in a row. What is the expected number of total tails he gets before this happens? First, let's note that as soon as Peter gets a tails, it's almost like he has, quote, reset his count. Therefore, we can construct 3 cases. By the way, first let's compute what is the total number of flips he gets before this happens. Then we'll deal with the tails parts later. Let's represent x as our answer. First, case 1. Let's assume Peter is extremely lucky and he gets 2 consecutive heads. The probability of this is 1/2 times 1/2, and this will take 2 flips. The expected value is simply 1/2. Let's look at the second case. A tails appears. This can be thought of wasting a flip because now we have to reset. The expected value of flips to reach our goal is still x. Remember, x is the total number of flips he gets before he gets 2 in a row. So the probability of flipping a tails is 1/2 times x plus our 1 wasted flip. Case 3, we get heads on the first flip and tails on the second. Again, we have wasted 2 flips. We still expect x more flips, plus the 2 we just wasted. The probability of this is 1/2 squared times x plus 2. So we set x to be equal to the sum of all our cases. Evaluating this gives us x equals 6. However, we are not done, because x is the total number of flips, not the expected number of total tails. However, we can simply note that the expected value of heads must always equal the expected value of tails because their probabilities are equal. Therefore, 2 times the expected value of tails is 6, and the expected value of tails before you get 2 heads would be equal to 3.